Let's talk a little more about sequences. The limit laws hold for the limits of sequences because a limit's a limit. So basically when we have limits applying to sequences, let's see what that means. If we have A sub n and B sub n convergent sequences and C a constant, then if we have the limit of the sum of two sequences, that is equal to the sum of the limit of each one. If we have the limit of the difference, it's equal to the limit of each one and then take the difference. If we have this sequence times a constant, the limit of that is the same as the limit of the sequence and then multiply by the constant. If we have the limit of the product of these, then that's the same as the limit of each one and then take the product. Same with the quotient. The limit of a quotient is the quotient of the limits. And if we have a power on this convergent sequence, the limit of this would be the limit of the sequence and then raised to the power, provided that the power was positive and the sequence was also positive. And then we also have, if we're looking at a sequence that's just a constant, that limit is going to be the constant because that's going to stay constant. So we have a squeeze theorem for sequences. If we have a sequence A sub n and it is always less than or equal to this sequence B sub n, we have another sequence C sub n that is always greater than or equal to this B sub n, and if the limit of A sub n equals the limit of C sub n, then we know this function that's squeezed between them also has the same limit. So here we have our sequences, and our B sub n is always in between or equal to the A sub n and the C sub n, and so if the limit of A sub n and C sub n are equals L, then the limit of B sub n also equals L. Now we're going to use that idea to prove this theorem. If we have the limit as n approaches infinity of the absolute value of the sequence and that equals 0, then the limit of the sequence also equals 0. And so the proof of that is essentially this. If, given the absolute value equals 0, then we also know that the negative of the absolute value also equals 0, because we could just multiply both sides by -1. And since we have these two equaling 0, and this A sub n will always be between these two values, we know that one also equals 0. So this is going to be helpful because we may have a sequence whose terms might be positives and negatives, and it might be a little harder to determine, but if we take the absolute value of those terms and the limit as n goes to infinity of this absolute value is 0, now we know that the limit of the sequence itself is also 0. So as an example, let's look at this sequence and does it converge or diverge? And as we look at it, this is going to make it alternate signs. But if we looked at the absolute value of this, if we took the absolute value, we wouldn't have to worry about that, and we would just be looking at the limit as n goes to infinity of n over 2n plus 1, and we could multiply numerator denominator by n, and we'd have the limit as n goes to infinity of 1 over 2 plus 1 over n, and we know that this is going to go to 0, and so the limit equals 1/2, and therefore this other sequence, the one that this original sequence, also converges and to 1/2. Now just some terminology for sequences. As we look at this sequence and we let n go from 1 to 2 to 3 and so forth, we see that this sequence, the terms are increasing. Each one is larger than the one in front. So we call that an increasing sequence, and that is just simply when any term is less than the term after that. So the A sub n is less than the A sub n plus 1 term. Now, similarly, if we looked at a sequence like this, we see that each term is less than the one in front. So this is called a decreasing sequence because A sub n is greater than the term after it. So these terms decreasing. And we call the sequence monotonic if it's always increasing or always decreasing. Mono means one, and it means it does one thing. It either always increases or always decreases, and if it's either of those, we call it a monotonic sequence. Now, a bounded sequence. If we have a sequence, it is bounded above if there is a number m such that a sub n is less than or equal to m for all n greater than or equal to 1. So it just simply says all of the terms in the sequence are less than or equal to m. And then it's bounded above. Here's a picture, this first one. And we can come up with an m, and all of the terms in the sequence are less than or equal to that. Looking at the second part, it is bounded below if there is a number lowercase m such that a sub n is greater than or equal to m for all n greater than or equal to 1. So this one is saying it's bounded below if I can come up with a number little m such that all of the terms in the sequence are greater than or equal to that value. Then, if a sequence is bounded both above and below, we just simply call it a bounded sequence. So we can have a bounded above, a bounded below, or a bounded. So here is a decreasing bounded sequence. We can see that there's a number and that none of the terms are greater than. We can see there is also a number that none of the terms are less than, and so it is bounded, but it is decreasing because each of those terms is greater than the one to the right of it. Here is an increasing bounded sequence. We can see that there is an m such that none of the terms in the sequence are greater than that, and we can see there is a little m such that none of the terms in the sequence are less than that, yet this sequence is increasing because any term is less than the term to the right of that. So now we have some terminology for these sequences. Let's ask a few questions. If a sequence is bounded, will it always converge? We saw an example a minute ago that was increasing but bounded, and so it did converge to that m, but here is an example to show you a sequence. This sequence is bounded. It never goes above 1. It never goes below -1, but it does not converge because it's alternating here between -1 and 1. So the answer is just simply having a bounded sequence does not tell you anything about convergence. If a sequence is monotonic, will it always converge? Now, what did monotonic mean? It's always increasing or always decreasing, and we can easily see then that we don't know about convergence because here's an example of a monotonic that does not converge. We could also have an example of one that did. So what if it's bounded and monotonic? Will it always converge? So here's a sequence that is bounded, so it won't go above a certain m and it won't go below a certain little m. It's monotonic. In this particular case, it's always increasing. Well, will this converge then? We can't have that case where we saw that bounded didn't converge, where it went between -1 and 1, -1 and 1, because it's got to be monotonic. So this one looks like it probably will. Answer is it does. We have the bounded monotonic sequence theorem, which says a bounded monotonic sequence converges, and that's going to be useful for us. If we want to know if a sequence converges and we can show that it's always increasing or it's always decreasing, and we can show that it's bounded, then we know it does converge. So if we look, here's a couple of examples. This one will converge, and this one will also converge. Let's look at a proof of this theorem. So suppose we're going to look at the increasing one, and then the decreasing one is analogous to this. So suppose we have a sequence that's increasing and bounded. Well, since it's bounded, the set S, which is the terms such that they're greater than or equal to 1, has an upper bound. So if we look, here is our sequence that's increasing and bounded, and there will be an upper bound. Here's a lower bound, m, but since it's increasing, it will also have an upper bound, m. By the completeness axiom, which has to do with there's no holes in the real numbers, there's going to be a least upper bound, and we're going to call that L. So there's several upper bounds, numbers that it will not be greater than, but there's a least one of these, and we're going to call that L. Now, given epsilon greater than 0, L minus epsilon is not an upper bound for S. Now, if we think about that, if L is the least upper bound, then if we take L minus epsilon, it is not going to be an upper bound because L was the least upper bound. And if we took L and we subtracted a positive number from it, it is not going to be an upper bound. There's going to be some terms in this sequence that go above L minus epsilon. So therefore, we can find an n such that when we get this term, it's going to be greater than that. There's going to be these terms that are above that L minus epsilon. So we can find an n such that that's the case. But remember that this is an increasing sequence, so if we take a sub n greater than a sub n sub capital N for every n greater than capital N. So basically what this says, because it's an increasing sequence, for any n's greater than this capital N, the terms are going to be greater. So we can replace this a sub capital N with an a sub n, and this inequality will still be true. So a sub n is going to be greater than L minus epsilon. Well, so now we could move this, and we could just do a little bit of juggling, put the epsilon here and then turn the inequality, and we know that this difference is going to be, because L is greater than a minus n, is going to be positive, so greater than or equal to 0, and then that's going to be less than epsilon based on what we just found here. So we could express this as the absolute value here is less than epsilon whenever the small n is greater than capital N, and therefore that was our definition of what we needed to have this L be this limit. So the limit as n approaches infinity of a sub n equals L. So as long as we have that condition of it's bounded and it's increasing, and we could do an analogous thing for decreasing, so if it's bounded and monotonic, it will converge, it will have a limit.